So I'm Arturo Flores. I'm one of Tyson Oxner students at Oklahoma State University, and today I'm going to present a little bit of what we have been doing, which we decided to title Exploring the Relationship Between In-Situ Soil Moisture and Remotely Sensed Vegetation Indices. I'm going to start with the generic idea that we have all seen, and is that soil moisture is a key variable for hydrology. It controls plant growth, weather, runoff, blah, blah, blah. We know like the story here. But what I want to highlight is that soil moisture is not the same at all scales. If we look at the field scale, we want to know where do we need to irrigate, how much, where can we drive our machinery. But if we look at the mesoscale, we might look at soil moisture more of, okay, we start to do some policy making, or do we need like a warning system for drought, landslide? And we come back at how do we get soil moisture data, and usually we do it at point scale. So we still have to find ways in which we can bring this point scale to field scale or even to the mesoscale. And that's where our challenge and motivation comes into play, which is how are we going to translate point observation data into something actionable? And we need to follow two steps to do this. The first, of course, we need to measure the soil moisture somehow, which luckily for us in Oklahoma, it's already been done across the whole state, but the Mesonet, and thank you, they do a great job with quality control and continuous data. And then we need to find a way in which these points, we can bring them into something that we can use. Like point observation, not really useful if we are like in neighboring fields across or far away from a Mesonet station. So we need to find a way to upscale to field, watershed, or even to the state level. In Oklahoma, we have something that is called the OASIS, which is the state's automated mapping system. It's just a system that uses Mesonet data, precipitation data from the National Weather Service, and some sand content maps from Surgo to provide us with daily maps of soil moisture at 5, 25, and 60 centimeter depth. So we feed like the method works, we feed a regression model between this data, we create the residuals, and then we add these two maps together, and we end up with a soil moisture map that has like a little bit more spatial detail than just the regression map. This has been cross-validated before, and this system provides an accuracy of about 6% volumetric water content, which is a good product, but still it has some limitations. That is where our opportunities come into play. The first limitation is that, yeah, there are Mesonet stations everywhere, but all of these are measuring soil moisture under grassland, which for agriculture might be like a big limitation. If you look at the map in the middle, you see that the west side of Oklahoma is dominated by prairies and irrigated cropland. But if you go to the east, you start seeing more of pastures and forests. So I put two contrasting examples here. The one on the left is the Altus station located in Jackson County. It's that little dot in the middle of the screen. That's the Mesonet station. And you can see that it's surrounded by irrigated cropland. And you can even see some of the irrigation canals in there. And then on the right image is the Antlers station in southeast Oklahoma, which is, I think, inside like a pasture, but is surrounded by forest and some other kind of cropland. So what I'm trying to say here is that, yeah, there's Mesonet everywhere, but there's a lot of land cover that is not covered by this Mesonet. So it's not that the Mesonet data is wrong, but we should be careful of how we make use of all of this. And the second limitation of the OASIS system is that even though it has a 800-meter spatial resolution and is significantly finer than many remote sensing products, it's still too coarse if we want to use it for field applications. So the red circle that I show here, it's a 1,000-meter radius from the station, is the same outer circle that you're seeing here. And from OASIS, we can see that for the Altus station, the system is just telling us that for around 6 square kilometers, soil moisture is less variable than 1%. So we probably know that's not accurate. And similar case with the Antler station. we were able to test two improvements that we can make to this mapping system. And the first one was to increase the spatial resolution from 800 to 250 meters. And that just requires us to get some new maps from the Surgo database. And the second improvement, we included NDVI as a new regressor. So we wanted to see if we could capture some of the vegetation and soil moisture relationships. And NDVI, we got it from MODIS. That's why we use the 250 meter from the sand map as well. Okay, the first interesting result was that just by increasing the resolution of the sand map, we were able to see new patterns. They don't vary as like the same with the land cover, but we start seeing that sand is bringing some of that variability in, and it's just highlighting the influence of soil morphology on moisture, on soil moisture. It's not really any vegetation effect. But then when we include NDVI, we found something we were not really expecting, and is that NDVI is only or mostly significant to predict soil moisture during the growing season, but only at 60 centimeters. So what you're looking at here, it's the percentage of time that each of the variables on the x-axis were significant for the 4 seasons and 3 depths, and the colors is just green is when the median p-value was above 0.05, no, below 0.05, and the red one is when it was above. And I just want you to focus on this, on these two little squares that is just telling us that NDVI was significant for the 60 centimeter depth in summer and spring. And when we put all this together, we end up with maps that look like this. I'm showing here soil moisture at 60 centimeter depths for a random date in 2017 in Jackson County. And what you see on the left is the original OASIS methodology, but with an increased resolution of 250 meters. And as you can see, there's some variability. You can see some patterns, but it's mostly landscape morphology and soil morphology effects. But then on the right, you see when we include the NDVI, we start seeing some crop-like features like square fields. And then if you look in the middle, there's very high moisture content. And this is an irrigation district in the area. So yeah, NDVI is bringing something that just soil morphology and precipitation is not. But still, we have some future work to do. And first is we need to validate this new approach, because all we can do now is cross-validate it with grassland from the Mesonet, but we need to see how accurate these predictions are for cropland or forest or any other land cover. And maybe we can include other remote sensing products like Sentinel or Landsat. Maybe we should sacrifice the temporal resolution of MODIS for finer spatial resolution of these two products. And that's what I had for you. This is a QR code, which I tested early today and it been deactivated, but you can go online and look for Oklahoma mapping system and you can find it easily. And that's just a picture of a Mesonet station in the beautiful Oklahoma Panhandle. So thank you.